name's Curtis Champion and I'm a third year PhD based down here at the University of Tasmania in CSIRO, right down on the other side of the world from where you are now. And I'm supervised by the lovely Greta Petzel, who's present on your end, and along with Sean Tracy and Alistair Hobday. And I'm going to be talking about methodologies for measuring distribution changes, particularly focusing on spatial modelling considerations and approaches. So just to give a quick overview, I'm going to begin my talk by discussing range shifts in marine fishes from Australia. And although I know Greta's touched on this a bit already, I'm going to really specifically just focus on the methodologies that have come out of the Australian literature and have been used to measure these distribution changes. I'll then move on and hone in on some habitat suitability models, and I'll specifically provide a very basic introduction to these. It looks like there's some great talks later on in the afternoon over there that will probably get a little bit deeper than I will on those, but I just want to provide somewhat of an introduction to those. And then I'm going to step through a few considerations and approaches for measuring range shifts with habitat models, and I'm going to do so using some of mine and Greta's work that we've been doing over the last 2 years in my PhD. And then finally, again using an example from our work, I just want to discuss one approach for supporting fisheries climate change adaptation using habitat models. So it's a little bit of a big mixed bag, and I'm going to start with the Australian context and step through some methods and then move into some habitat models and how to use them to support fisheries adaptation. So down here in Australia, it's quite a unique oceanographic setting. We have two poleward flowing boundary currents. So with the current climate of ocean warming, we have this twofold effect where we have these poleward penetrating boundary currents that are indeed flowing further south than in the past, and that's coupled with regional ocean warming. So this twofold warming effect. This is particularly prominent on the east coast of Australia. So if we zoom in on that little box around Tasmania, which is a known ocean warming hotspot, and look at sea surface temperature data for about the last 24 years, we see if you go across each month, you'll see that sea surface temps are increasing. And the cumulative effect of this is that nowadays we have more months per year that are warmer compared to the past. And that's really culminating in a lot of distribution changes in the marine environment, and these tend to garner a fair bit of media attention down here because about 85% of our population lives on the coast, and we have avid coastal communities and very keen recreational anglers, so there's a lot of eyes on the water, and this tends to gain quite a bit of media attention when species from the north turn up in unlikely places. If we really drive now into the published literature, and this is something that Greta, along with Connor Gervais and myself, are just starting to look at, was a literature analysis just focusing on Australian distribution shifts in the marine environment. I'm just looking at fishes here, and we have about 69 species identified from 15 studies. And if we look at the methods that have been used for these fishes and these studies, we see that qualitative assessments really dominate the majority of fishes that have been identified. And we step down to see underwater surveys coming in second, moving along to fishery independent surveys that are essentially recruitment surveys and citizen science, and then down the bottom some species distribution models. And then if we look at the studies, out of those 15 studies, we see that underwater surveys typically dominate, and then the other methods are around 1 to 3 studies. That's only for identified fish distribution changes, and what we've also been doing down here, and I'm sure like other places around the world, are also moving into the future and doing future projections. So predicted fish distribution changes in the future, we have 68 species that have some kind of evidence supporting future distribution shifts. And they come from only 5 studies. So if we do the same thing that I did on the last slide, and we look at the fishes versus methods, we now see quite a different pattern. Well, obviously, because we can't actually go into the future and go diving and look, so we're looking at different methodologies here, and species distribution models really come out on top here for both fishes and studies. So if we compare past distribution changes in fishes from around Australia versus future shifts, we can see that the only common methodology between the two are species distribution models. And these models are what I'm going to argue are quite important because they provide the capacity to assess both past and future distribution changes, and therefore they play a key role in anticipating and adapting to future changes ahead of time, which is particularly relevant for our valuable industries such as fisheries, both commercial and recreational. So that was the background about the methods that have been used in the Australian literature to study distribution shifts in fishes. Now I'm just going to touch on species distribution models because they have come out as quite important in the literature search, and basically these are quantitative tools that estimate areas of suitable environmental habitat for a given species, and therefore they provide some kind of an estimate of locations where species are likely to occur relative to areas where species are unlikely to occur. And I apologise, I'm not familiar with who's in the audience and what level of statistical modelling might be there, so I'm just taking the most basic approach at introducing these models. But they essentially aim to make predictions through time in the context of studying distribution changes. We're aiming to make distribution predictions through time, like you can see on this slide here, multiple predictions and then measuring changes using these spatial predictions. So there's been two main approaches for species distribution models, the first being mechanistic models, which rely on having some kind of understanding about how a performance metric, be it activity or swim speed or anything else, oxygen consumption, performs against a given variable. So these are most commonly undertaken in the laboratory, and the assumption is that laboratory relationships hold true in the field. However, with the emergence of infotech, like fancy tags that you can put on animals, you can now get these relationships from animals in the field and parameterize species distribution models that way. By far, the more common approach has been a correlative species distribution modelling approach. So those green circles on the left with the little animals in them, that represents animals in one place at one time, so an occurrence record of a species, which is then matched with a suite of environmental data, be it temperature, salinity, dissolved oxygen. And those relationships can be related in a bunch of different ways, from statistical or machine learning algorithms, the vast diversity of correlative models that can handle these data types are very suitable. But what the result is that once you have the model calibrated, all you need are the environmental data to then begin to make predictions about where a species may occur. And the examples that I'm going to step through soon will really focus on this second correlative species distribution modelling approach, the more common of the two. But it's important to keep in mind that the goal is to identify a predictive relationship between a species distribution, which is typically quite hard to measure. Generally, we find it quite difficult to get a really solid grasp on where these marine fishes are and where their boundaries are with great accuracy. So what we're trying to do is choose a variable that's far easier to measure, such as sea surface temperature, and relate it to that distribution. So a key point to keep in mind is that habitat suitability models or species distribution models predict the distribution of a species' preferred environmental conditions and not the distributions directly. So we've got one variable there on the x-axis that might be an environmental variable that's easy to measure, and an occurrence record that might be harder to measure, and we're trying to relate something that's easier to measure with something that's more difficult to grasp. So for that reason, most of the scale bars will be accompanied by terms such as oceanographic habitat suitability or environmental preference, and not the term species X distribution. So that was the little background in species distribution modelling. Now I'm going to step through some examples from the work that Greta and I have been undertaking in southeastern Australia, just to highlight some considerations that should be considered when using these tools, and a couple of the approaches that we've used to overcome those considerations. And for all these examples, we'll be dealing with this species. It's the yellow-tailed kingfish. It's a very iconic species that is distributed along the southern coastlines of Australia and other parts of the world. But it's ecologically important. If the distribution of this animal is indeed shifting, we could be seeing novel predation pressure in different parts of southern Australia that we have not seen predation pressure from this animal before. And it's also associated with substantial economic revenue. There's a substantial commercial and recreational fishery around this species. And also socially, this is anecdotally Australia's favourite sport fish. So there's large groups of people that really enjoy recreational activities around this species. So if you take the ecological, economic and social implications together and consider potential distribution changes in this animal, it sums to an inventory of potential threats and opportunities if its distribution is changing. So to develop this kingfish habitat model, just going to step through how we went about it and highlight some of the key considerations that went into it and approaches to overcome some of the things that were required to be considered. So if you remember back to those green circles on the previous slide, we essentially needed a lot of records of this animal in space and time. And we used a large citizen science database of about 1,300 records that had a temporal range from 1996 to 2015. And to those records, and to also a large suite of pseudo-absence records, which were required for the modelling approach that we employed that I'll discuss in a moment. We matched satellite-sensed environmental variables, and there was a large suite of these that we matched. I've got 3 here that ended up coming out as significant predictors of the distribution of this animal, and we have sea surface temperature, sea level anomaly, and eddy kinetic energy. These were related in a statistical model, so by having the blue dots, which were the occurrence records, and the pseudo-absence dots that I mentioned, essentially gave us a binomial response variable. We had zeros and ones in our data set, and we were able to tease out these relationships with environmental data. So you can see with sea surface temperature, this animal had a peak occurrence around 21 degrees, essentially a positive relationship with sea level anomaly, and a more complex relationship with eddy kinetic energy. Given the nature of this data, we chose to use a generalised additive mixed modelling approach, which handled the data well. Any form of correlative model can really be used as a form of species distribution model, but this was the form that best fit our data. And with that model sorted, we were able to start making spatial predictions of the oceanographic habitat suitability of this animal. So this is how we've gotten to this point. We're essentially armed with a model, and we can make spatial predictions about where this animal is likely to occur relative to where it's not likely to occur. We're interested in measuring distribution changes here, and that's what I imagine a lot of the last day and the first half of your today has been discussing. However, the first key consideration is really which habitat suitability value might be representative of a species range boundary. If we don't have a handle on a specific value, it's hard to measure a change through time. And as I mentioned earlier, these considerations are rather universal. The approaches are not necessarily. They'll be specific to the data available for the animal and the system, but I just want to give you a flavour of how we actually went about it. So essentially, we're trying to take a habitat suitability projection that's on a scale from 0 to 1 and identify a value along that scale that we consider an accurate or reasonable estimate of the boundary of this species distribution. So Greta may have spoken yesterday about the wonderful citizen science initiative that she's developed down here in Australia that's called REDMAP, the Range Extension Database and Mapping Project. And really it's an ideal data set to look into species range boundaries in Australia. So what we did is we pulled all the occurrence records for kingfish out of that database, and they were not used to train the initial habitat model. And we made daily predictions of suitable oceanographic habitat for kingfish for every record that was in that database. And we extracted the values. So that box plot on the left are all the values of habitat suitability from the REDMAP database. And I'll reiterate why REDMAP's a great database is because we're actively looking for animals at their range edge. So we should be finding them in relatively low areas of suitable environmental habitat. So what we essentially did was just adopt the minimum value that came out of that data set. And of course there are some limitations to this, but it is a neat little way at least to get some grasp on what value might constitute a species range boundary using a habitat suitability model and a small independent data set of records that are likely to have come from the range boundary. So with that in mind, we could then produce these sorts of linear models that show change in that oceanographic habitat suitability value through time. And that's how we went about developing the relationship that you see in column B. And with that approach, the combined approach of the habitat suitability model and the independent data set from the REDMAP database, we were able to estimate that yellowtail kingfish from southeastern Australia has shifted poleward by about 108 kilometres a decade over the last 25 years or so. The next key consideration that I'd just like to bring up, and it's something that I think is quite important if we're looking to start to attribute distribution shifts in marine fishes to climate change, is the influence of natural climate variability. So of course there's intra-annual variability, so we have seasonal, weekly, monthly natural variability in species distributions. And we also have natural intra-annual variability, so that might come from something like El Nino, southern oscillation, and that's known to affect the distributions of, say, large pelagic fishes. So in that same analysis I presented on the last slide, these trends in these plots were actually fitted with linear mixed effects models, and I just would like to quickly highlight the utility of a mixed effects model for accounting for natural variation versus the climate change signal in a species, in the change in distribution of a species. So it was possible to fit month and El Nino southern oscillation state, so that's both an intra-annual and inter-annual source of natural variability as a random effect in these models, which essentially imposes a dependency structure in the model and allows us to estimate the trend through time with more accuracy, not completely independent of those sources of variation, but at least accounts for them and allows us to estimate those rates of change more accurately. So while this is not a golden bullet and doesn't fully account for natural sources of climate variation and get to a climate change signal per se, it goes part way of that. And it's something worth considering when we are definitely talking about distribution shifts. There's both natural and anthropogenic sources of climate variation. So we're not at the point of direct attribution, but we're part way, or we feel like we've taken somewhat of a step towards accounting for natural climate variability, which is something that I'd argue is quite important to consider. Moving forward, and indeed moving into the future, I'm now talking about future environmental habitat forecasts. And it's quite a basic point to make, but when we are using habitat suitability models, there's often a tendency to pack as many predictor variables into these models as possible. So in this model, we've got sea surface temperature, sea level anomaly, and current speed. But if you're looking to make future habitat predictions, you'd want to be quite sure that these sources of data are available as forecasts into the future. So one of the limitations of future forecasts of habitat models has just simply been the availability of predictor variables, and 5 to 10 years ago, most habitat forecasts into the future were simply based on sea surface temperature alone. Improvements in oceanographic modelling now means that we do have future forecast variables like sea level anomaly and eddy kinetic energy, and we can start to now build up more accurate habitat suitability models for future forecasting purposes. As I mentioned, it is a basic point to make, but it's not necessarily that advantageous to develop the most complex habitat suitability model if your objective is to do future forecasting for, say, the purposes of climate adaptation. You can see the small little time series, I suppose, that's up on the screen is the same habitat model, but we've actually now pushed it into the future, and it's developed now for a purpose of fisheries adaptation. So we've restricted the analysis to the continental shelf only, where the majority of fishing for that yellowtail kingfish species occurs. Similarly, like when we identified an estimate of the range boundary of this animal, we wanted to differentiate between suitable and unsuitable environmental habitat. And this has been a long-standing conundrum for species distribution modelers worldwide, and many of the black box species distribution modelling packages that are available in statistical computing programs often simply adopt 0.5 as a threshold value to differentiate between suitable and unsuitable habitat, because it's often necessary to convert these continuous variables, this habitat suitability on a scale of 0 to 1 to something that's binary for the purpose of, say, informing fishers or other stakeholders to allow them to adapt, because a habitat suitability value on the scale of 0 to 1 may not necessarily be as informative to them or as interpretable as a simple binary yes or no, fish here, fish there, no fish there, no fish here, for example. So our approach to making that process a little more ecologically realistic was to pull another independent data set of kingfish records out of a repository which is called the Atlas of Living Australia, and we essentially made habitat predictions, daily habitat predictions for all of those records, and we created the distribution in little plot A there, and again just adopted the minimum value as our value to separate that continuous habitat suitability into a binary presence or absence, well, likely presence or absence of that animal. And that is just a small approach to the consideration of how do you divide habitat suitability from a continuous product into something that's binary. And that was important to move forward. And for the next slide, which is now moving slightly away from the considerations of habitat suitability modelling and more towards climate adaptation and using these models for strategic adaptation by recreational or commercial fishers that may find this species valuable, this or other species valuable. So the key consideration that I wanted to raise here was that future projections need to be easy for stakeholders to interpret if that is indeed the purpose. So in this paper that Greta and myself and my other two supervisors put together, we really steered away from providing those colourful maps and looked for something a little more simple. And we came up with the idea of temporal habitat persistence, and that is essentially the number of months per year that suitable habitat, defined as I just mentioned on the previous slide, exists for in each of these regions from southeastern Australia. And then we projected that through time, and we looked if the number of months per year that suitable habitat for this animal would persist. And in the northernmost bioregion, we found that it looks to be declining. The number of months per year suitable habitat it will persist is actually decreasing or looks likely to decrease, whereas in the three most southern bioregions, the cooler bioregions, we're seeing significant increases in the number of months per year that suitable habitat is likely to persist. Another quick key point that I'd mention here is that you can see the analysis was only pushed to 2040, and that's something that one of my supervisors, Alistair Hobday, and I'm sure others are really big on. It's about pushing analyses only out as far as you're willing to make decisions about them. So just really focusing on your decision-making timescale in your projections. You may say, well, why is that so important for stakeholders? Well, we really thought long and hard about temporal habitat persistence, and we think that it's analogous to opportunity. So in the north, we might have declining opportunity to target this very valuable species, whereas in the south, with more months per year of suitable habitat persisting, it looks like there may be increasing opportunity to target this species. So we sort of dubbed the term changing windows of opportunity as the little catch cry for the paper. And opportunity, as I mentioned, is definitely relevant to fishing opportunity. As people, off the east coast of Tasmania at that southern bioregion now may have more opportunity and potentially might like to invest in that expensive lure to target this species, or the commercial fishers from the very southern tip of the mainland might like to steam a little further south in the future to maximise their catch per unit effort. It's also somewhat analogous to ecological opportunity. So when we're considering range-shifting species, we're considering them across this pathway of arrival, population increase, and eventual establishment. And if the environment is indeed suitable for more months of the year, it could speed up this process and really allow self-sustaining populations of marine fishes to establish in novel environments. So the idea of taking a habitat suitability model and converting the output to something that's relevant to stakeholders and easy to interpret, I think, is not something that should be understated, because this is really where a lot of the value of this quantitative approach lies. And I think this slide really highlights that both social and economic value in the form of fishing opportunity and ecological value in the form of interpreting a range shift pathway. So that's basically all I really wanted to contribute, and I know I might be a little under time, but I'll just quickly sum up. And so I started off by demonstrating or highlighting the Australian context, and including the range of methods that have been utilised to measure range shifts in fishes here. I then went on to describe why species distribution or habitat suitability models, I use that term interchangeably because they're essentially the same thing, why they're important, and that was basically because they have the capacity to address both past and future distribution changes. Then went on with an example-based pathway and highlighted that independent data sources can be used to compare your predictions with to define things like range boundaries or differentiate between suitable or unsuitable habitat when you're searching to identify a binary output from species distribution models. And also highlighting the need to account or somewhat consider sources of natural climate variation if you are seeking to use those models to try and look at direct attribution to anthropogenic climate warming. And then the simple but I think necessary statement that you need to ensure that your predictor variables are actually available as forecast products if you do wish to start predicting into the future. And then I just wrapped up by finally considering the value of converting outputs to metrics that are of relevance to stakeholders, because that's really where the climate change adaptation comes in. So thanks very much. Oh, they're the two papers that those examples came from, and thanks very much for allowing me to participate remotely. Cheers.
Thank you, Curtis. That was great. I should thank you too for staying up so late, to appease our schedule. No
worries.
Yeah, we have time for a couple of questions.
Hi, Curtis. Can you hear me? It's on. It sounds on to me. Can you hear me?
Yes, just. I'm listening intently.
Okay. First of all, awesome talk. Thank you. That was super interesting. I have a couple questions. I have so many, but I'll just start with one, which is that I think maybe I missed it, but I like this idea of trying to figure out basically how to convert this continuous habitat suitability index into actually defining a range boundary of 0 or 1. But I missed what the result was there. What is it not 0.5? You said everybody uses 0.5, but that might not be right.
Yeah. It's been assumed that you can use 0.5 as the value with which to separate that continuous output to a binary product. And all I'm really saying there is that the opportunity to utilize independent data sources that weren't used to train the model and compare those with your habitat projections to define more ecologically realistic values to do that separation is a worthwhile step in the modelling approach, and something that really increases the ecological realism of the output. And then the result was that I used those values to model a range shift through time.
So were they different from 0.5 then?
Yeah, most certainly. When I was seeking to identify the range edge, the value that came out was 0.06. And then when I was using a far more conservative estimate, just to identify what would be an ecologically realistic point with which to separate that continuous output into a binary product, it was 0.19 for my species in my system.
Okay, so that means we're greatly overestimating ranges if we use 0.5, when really 0.1 is more suitable, more realistic.
Yeah, yes, or we're underestimating rates. Or the rate of range shift is independent of the value used, but yeah, the spatial difference will most certainly vary. So utilizing a larger value will essentially give you, will be actually more conservative, the range shift. Say if it's a polewood range shift, your end result would be closer to the equator.
Yeah, cool. Okay, and then maybe a follow-up question for later, but just I'm curious how the, basically whether there are certain species traits associated with differences in the habitat suitability score that defines a range boundary.
Yeah, species traits would be very interesting to look at. That'd probably be another way that you could tackle that question about which value might be more ecologically realistic.
Cool. Thank you.
Okay, maybe one more question, and then we move on next one.
Hi, thank you for your presentation, Curtis. The question I have is, I don't really know what the citizen scientist observations are, kind of in terms of, are they're just presence-absence observations by some strata from south to north?
Yeah, they're presence-only observations by a member of the public, and they're photographed and verified by a team of scientists.
Okay.
So, yeah, just a single point in time.
Got it. So, if you start thinking about distribution shifts and sort of potential opportunity lost or opportunity gained, it might be an interesting exercise to look at the distribution of fishing effort over your suitability map. Is that something you might want to consider in the future?
Yeah, most certainly, and that's a great point. The data set that I actually used to parameterize my habitat model actually came from a citizen science data set, a very, very large tagging database. And the way that I accounted for fishing effort in the database, which was not present, there was no information about fishing effort, but I simply included year as a random effect in the habitat model, which allowed for different variation among years. It's sort of a proxy for fishing effort, but I certainly agree it's almost as if I've used fishing effort rather than the location or distribution of the animal. But such is the nature of dealing with these sorts of data sets.
Thank you.
Thanks for the question.